This video will introduce and explain some basic uranium enrichment concepts. To successfully apply safeguards to a uranium enrichment facility, we must first understand how enrichment works. Although there are many enrichment technologies and an even greater number of facility designs, there are some concepts that hold for all enrichment facilities, no matter what technology is used to accomplish the enrichment process. The most basic component of the enrichment process is the separation element. This is a basic element that receives a single input stream at a certain level of enrichment and produces two outgoing streams, one that is enriched relative to the input stream and another that is depleted relative to the input stream. The input stream is referred to as the feed. In the diagram we see here, it has a mass flow rate of F kilograms per unit time. The enriched stream is referred to as the product, with a mass flow rate of P kilograms per unit time. The depleted stream is referred to as the waste, or tails, and has a mass flow rate of W kilograms per unit time. NF, NP, and NW represent the uranium-235 fraction in the feed, product, and waste streams, respectively. When we look at a single separation element, we want to know how effective that separation element is at increasing the enrichment level of the feed stream. This effectiveness is known as the separation factor, and we calculate it by taking the ratio of the concentration of the product stream to the concentration of the waste stream, as we see in this equation. Another key characteristic of our separation element is its throughput. This is the mass flow rate at which the uranium feed can be processed. It is the total mass of material passing through the separation element per unit time. For most enrichment technologies, the throughput of a single separation element is very small, meaning that one separation element is unable to process large amounts of material at a given time. When we see pictures of gas centrifuge enrichment facilities, we almost always see large numbers of centrifuge elements interconnected into complicated configurations. Separation elements are first arranged in parallel, allowing material to be enriched simultaneously. This is done to increase the material throughput. These parallel arrangements of separation elements are called stages. Stages are then connected in series to form cascades. Basically, the enriched output stream of each stage becomes the feed stream for the next stage in the series, and so on. As the stage increases the throughput of the enrichment process, cascades allow for a multiplication of the separation factor of the separation elements in order to achieve a higher product enrichment. One final concept we should discuss before we go on to compare the different enrichment technologies is the separative work unit, or SWU, which represents the electrical, mechanical, and chemical work that goes into the enrichment process. The energy consumption of an enrichment facility is usually given in kilowatt hours per SWU. Generally speaking, it takes approximately 100,000 SWU to produce enough low-enriched uranium to fuel a light water reactor for a year of operation. It takes around 200 SWU to produce a kg of uranium enriched to 90%, and approximately 5,000 SWU to produce a significant quantity of weapons-grade material. This means that an enrichment facility intended for the peaceful uses of nuclear energy has more than enough capacity to produce materials for nuclear weapons. This is part of the reason why it is critical to safeguard commercial uranium enrichment facilities to ensure that plant material is not being enriched beyond the limits imposed.